Hello, everyone. Hope everyone is doing good and having a good learning journey with us. This video is going to be a complementary content to the course of Python for oil and gas. And in this video, I will teach you how to create a pipeline design and do some basic hydraulic analysis or hydraulic design for a specific length of pipe. So before we start, let me just give you a brief background about this topic itself. The topic itself, it's not that complicated. Usually you have 2 points in pipelines. The first point is going to be the source, meaning the oil is going to flow from or any fluid, as a matter of fact, is going to flow from, for example, from left to right. And the left is usually known as a source, and the right is usually known as the sink. The sink meaning that this is the place where the oil ends or the fluid ends, as a matter of fact. We have some few points that actually control the flow or the flow phenomena. So the first thing is the pressure at the source. We have the pressure at the source, and we have the flow rate at the source. By the way, if you have a specific flow rate, let's call it Q1, entering from the source in this direction, the same flow rate Q2 should be on the outside, meaning that Q in equals to Q out. This is known as the conservation of mass. And let's go back to the parameters in the source, and you have something called temperature. So those are the three basic inputs you usually use. And we have something else. It's actually is the ambient temperature of the pipeline itself, meaning that the air temperature around the pipeline. So these are all the basic informations you need. Plus you need all the information about the pipeline, like the length, the diameter, and the friction factor, and everything else. Plus you need the fluid properties like the API and the water cut and the GR and the gas specific gravity. So all those basic things. So without further ado, let's go ahead and try to program a solution that designs this hydraulic calculation for us. So it should be very simple and basic. So we will import matplotlib.pyplot as PLT. So this is going to be our plotting library of choice, by the way. And second thing we need a library that might be new to you, and the library is called PSAPY. So open and command the prompt like so, and wait for it to load. So what you're going to do is inside and command the prompt, you will type pip install PSAPY. This library actually provides correlations for you to do some hydraulic analysis. Basically, this library is created for production optimization, but you can use it for whatever purpose you like. And click enter, and you should have this library ready. So once you got that library installed, let's go ahead and import some of the correlations. So we will go and use import PSAPY dot. By the way, PSAPY basically has actually two correlations. You have the Beggs and Brill, and you have the Hayes-Jordan-Brown. By the way, if you are not familiar with these two actually they used to be one of the most famous correlations. Beggs and Brill actually used on almost all angles. It's preferably used on horizontal pipe sections. Hayes-Jordan-Brown actually it's recommended for vertical pipelines, or actually they are recommended for wells. For this example, we will use Beggs and Brill. So once you import Beggs and Brill, let's give it an alias, which is BB. Okay, you can name it whatever you like. And once we do that, actually we're all set. We will define all the input parameters we want. So the input parameters, we will define them as dictionaries. I found this is the most appropriate way to define these. So we will have source. We will have something called pipe, which is the properties of the pipe, and another thing we have, it's called the fluid itself. So source equals to, in order to define dictionary, you can use either this or you can use this keyword dict, meaning that you are defining dictionary. Now the dictionary is ready to accept the properties that we are going to populate. So the pressure is 1500 and the Q equals to 20,000 and the temperature is equal to 80. This 80 is actually is Fahrenheit, so let's put the units. So PSI, stock tank barrel per day, and Fahrenheit. So these are the units. For the pipe, we have some basic inputs in the pipe, so we will define it as dictionary as well. So dictionary, let's define a length for the pipe, like so. The length is going to be 4,950. And the angle is going to be 0, meaning that this is horizontal. If the angle is 90, meaning that this is vertical. And any angle in between is acceptable as well. And the last and final thing is the pipe diameter itself. The pipe diameter, assume the pipe diameter as 6. So if you're applying this, please just copy the values that we have in here, or you can just refer to this project file that will be attached with the video as well. Now, the final thing left, which is it's the input parameters, which is the fluid. The fluid property is going to be dictionary as well. We will start with the API, which is the gravity density of the oil. We assume it 30. And water cut, I'll assume the water cut is 0, but you can use whatever value you like. Actually, I am putting those strict values because I created a Python project and compared my results to the Python project. That's why I'm sticking to specific values. And let's create GOR equals to 1200 and the gas gravity SPGR, which is in fractions, 0.64. So for the units are API degree. Water cut is actually it's in fraction. You have the GOR in standard cubic feet per stock tank barrel. And you have the gas specific gravity, it's in fraction as well. So hopefully everything's clear so far. Those are where actually all the basic inputs you need. So now what we need to do is, now we need to divide this pipeline into increments. So at each increment we will calculate the pressure. So but before we do that, let me do one thing. Let's just plot our pipeline in a PLT plot. So we will use PLT dot plot. So we will plot the X and Y as like so. So the X, we will assume the source starts from, for example, from 0 to, for example, 0, 0 to, let's say, 0, 100. So let's assume this is a line plot. Let's give this a run. Yeah, this is the plot itself. Let's assume this X, let's change X from 100 to 0. Yeah, it should be, by the way, it should be a straight line. The second Y should be 100 as well. Yeah. Sorry. So, but you get the basic idea. What we are trying is we are trying to plot the direction of the pipeline, but it's not that important. And let's continue. The first thing we need is we need to segmentize or divide our pipelines into specific length. So we will do one thing. We will create a list of pipeline range. So pipeline underscore range equals to a list of some range function we will use. So starting from 0 and ending at pipe, which is the dictionary for pipeline, ending at the pipeline length. So now you can see that's why we define the dictionary, because it's going to be a much more manageable way into manipulating the inputs. So this is the pipeline range. So before we do anything, let's go ahead and click run. And there we go. Now we have the pipeline range. If you are not comfortable with that range, you can just change the values to whatever you like. So the next step is we need to create a list that will hold all the pressure values for us. So pressures equals to this. And then we will create another list that will hold all the hold up value for us. Hold up. So this is the hold up, by the way, is the percentage of the water, or sorry, percentage of the liquid contained in the pipeline at a specific length. Hold up 100% means that the liquid is 100%. Hold up 30% means that the liquid is 30% and the gas is 70%, and so on and so forth. So this is the concept of hold up. So let's go ahead and create our loop. So the loop actually will use length. So for example, length in we will use this range which we created for pipeline range. That's it. Okay. Now we will need one thing. Whenever the pipeline length is 0, meaning that this is the source of the pipeline, the pressure is 1500. As you move away from the source, the pressure will be decreased. And so this is the basic idea. So let me just close this. Let's go ahead and do some calculations. So if length equals to 0, meaning that the pressure is equals to the source. So what we will do one thing, we will use pressures dot append. We will append the source pressure, which is source P, and that's it. And regarding the holdups, we have to assume a holdup value. By the way, I'm going to assume some arbitrary value. And let's assume a value of 50% holdup. Let's assume 50%. And you can assume whatever value you like. So let's go for the next part, which is else. Now, any length that's not 0, it's going to be calculated in here. We will calculate the pressure gradient. By the way, pressure gradient is how much pressure drop you will have per feet. Okay, actually it's going to be less than 1 usually, meaning that you are having pressure drop of less than 1 and per feet. So how to calculate that? By the way, that's very easy to do. You will let's create a gradient. Gradient equals to Biggs and Brill we just used dot pgrad. Meaning that we want to calculate the pressure gradient. And by the way, it populated all those informations, so we need to fill everything. So the pressure. Actually, this is one of the trickiest things we need to specify. But before we do anything, we'll go ahead and fill out all the rest of the information because they are almost static information. So the temperature, we will get the temperature from the source, or you can get the temperature from the pipe temperature. So everything, we'll assume everything is the same. And so temperature equals to source temp. The oil rate, we get it from source Q. Source Q. The water rate is 0. We don't have any water. The gas oil ratio is from source as well. Source. The gas oil ratio is from the fluid. From the fluid and GOR. The gas specific gravity or the gas gravity is from the GOR as well, from the fluid as well. So fluid gas underscore SPGR. So now you can see like the actual benefits of having dictionaries. Otherwise, you will have to like define bunch of values, and that will take up much beauty of your code. So oil gravity from fluid as well, which is API usually, and fluid API. The water gravity, by the way, just assume it 1 because we don't have any water. Otherwise, you should specify it, by the way. The diameter is in inches. So we will get the diameter from the pipe, diam, which is 6 inches, by the way. And the angle we will get it from the pipe as well. Pipe and angle. There we go. And let's go ahead and before we do anything, let's go ahead and do one thing. Double click on the pgrad itself, right click, and then use this line, go to definition. This actually will open the source file of this function. We need to do one thing. By the way, this function is already written by the people who wrote this library. But we need to do one thing. There is one thing missing in this function. On line 113, it should be the same number. Please add this line, which is comma, and then YL. YL actually is the value of the holdup. By default, you will find it like this. There is no value of holdup is being returned. However, it's being calculated, which is a good thing, but it's not being returned. So let's go ahead and return it using YL. YL is just the fraction of the liquid that's existing in the pipe. Click save. Please do not forget to click save. Once you do that, now the source file of this library is modified. Close this. Now we are calculated gradient, and we have something else called holdup. Let's go ahead and print everything just to check our work. So gradient equals to grad, and then we have holdup equals to hold. So let's go ahead and put an F. Yes, and everything should be fine. Let's go ahead and click run. Pressure is not defined, so let's go ahead and see why the pressure is not defined. Yes. And actually it's pressures, not pressure, that's why. And source is not defined. Source, because we are misspelling everything, that's why we're getting an error. P is not defined. Yeah, the only thing remain is actually is the pressure. So if you fixate the pressure on source pressure, for example, like so, this is going to give you a wrong value. In a minute, I will tell you why, but let me just run this. As you can see, these are all the results we got. If you can just take a close look, the gradient and the holdup, it's the same value for all the length of the pipe. This is not correct because at each specific length in the pipe, the pressure will change, will drop, and depending on that pressure, all those fluid properties is being calculated, and so this value should change with the assumed length. How can we do that? Now it's time to introduce a new variable called P current, which is the current pressure that the solver is using. So the starting value is going to be source pressure. Now we're good to go. In the else, once you calculate everything, let's recalculate this pressure and assign it. So how can we do that? We will go and write P current underscore current equals to the source pressure, which is the main pressure, the main pumping pressure, minus the gradient, which is the pressure drop per feet, multiplied by the actual length that you have achieved using the for loop. So multiplied by length, and that's it actually. Now we will assign, or we will use the P current, P underscore current, and let's go ahead and calculate everything. So click run. Now you can see, now you're having different values. Like different values is being generated each and every time. One thing is problematic with our solution is too many steps is being taken in the range. So let's go ahead and reduce this. We will give it 100 feet increment. Run this again, and that's it. Now those values are yours, your calculation values. Yeah, you can see is the values actually they vary. For example, the hold up starting is 53, which is 53%, and the hold up ending is 48%. So now our solution is correct. Let's go ahead and instead of printing everything, let's save all those nifty values. So pressures dot append, we will add the calculated pressure, which is peak current, by the way. And let's add the holdups as well. Holdups dot append. You open and close parentheses, and then you will put something like holdup. However, you have to multiply it by 100. That way it will be shown as 100%. And I think we are ready to do some plotting. Before we do anything, let me just create a subplot of the matplotlib. So, and plt.subplots. So axis equals to, so figure axis equals to this thing. Okay. Once you do that, now we have the axis, which is the main plotting axis. Let's go ahead and do some plotting with the axis. So axis dot plot. In the x-axis, we will provide the length, which is the pipeline range. By the way, the length, the x is going to be pipeline range all the way. And we have the y-axis, which is going to be the pressures we just calculated. Let's click run. Yes, for some reason it's not working, so let's go ahead and see why. Actually the subplots, we are missing S, and that's it. Yes, there we go. This is the pressure. It's 1500 at the starting point, and then we have something like 1225 or something. So this is the first thing, and let's go ahead and try to plot the second Y or the right Y. So let's go ahead and call it axis 2 equals to the first axis, and we will copy the X. So we will have like differing Y. So let's go ahead and do that. Axis 2 dot plot. We will be plotting the pipeline range. Let me copy this, and then we have the holdups. Everything should be working fine by now, and there we go. Now we have the holdups, and let's just give this a name and color. So color equals to holdup. I will give it a color red, and for the main one, the pressure, I will give it a green color equals to green. And now the only thing remains is giving label to each and everything. So label equal to the pressure drop, and the second one is going to be label equals to liquid holdup. There we go. Let's run everything, and there we have it. By the way, now you can see the holdup is actually, it's not the most correct value because in the first holdup we assumed like a arbitrary value. So let's go ahead and change this to 53, so it's going to be on the same scale. Run, and now much better. So the only thing remains is to do some adjustment or to show the legend itself. So figure dot legend. Now we are having legend as well, and let's go ahead and show the grid. Figure grid. Yeah, it's not working. does not have an attribute called grid. Let's try axis.grid. Yes, now we have the grids. Let's try to change the X and Y range of the holdup because it's being overlapped with the pressure itself, and I don't like that actually. And so let's go ahead and do that. So axis2 dot set underscore y limit, the y lim. So I will assume the holdup limit is starting from 0 and ending at 100. Let's give this a run. And there you go. Now you have a much sensible way into viewing like the holdup. But you can do one thing. Let's go ahead and plot the maximum holdup coming from the holdups list. Yeah, there we go. You can add just like 10 values to it. Yes, now you have your holdup. Yeah, by the way, you can do a lot of things with this. Let's go ahead and add the X label. So axis1 dot set underscore X label. Open everything and then just give it a name. So length in feet. Run this. There we go. The only thing remain is to give a Y axis. So set underscore Y label. We call it pressure